Welcome friends, in today's lecture we are going to study design of band brake. In previous two lectures we have studied design of long shoe brake and short shoe brake. That is, in 45 minutes I have completed both those previous lectures, and in this lecture in about 30 to 40 minutes we will complete band brake design. That means in 1.5 hours you will able to study complete brake design. So let us start with the design procedure for the band brake. You can even watch this video in fast forward speed to save your time. Band brakes are basically divided into two types, that is simple band brake and differential band brake. We will start our discussion with simple band brake. If one end of band passes through the fulcrum, let us say this is the fulcrum, it is known as simple band brake. The requirement is that one end of the band, any one end should pass through this fulcrum. Now in the figure you can see this is the lever, then this is the band complete, and inner circle is the wheel or ring or whatever it may be, whatever be the shape of this drum rotating part. And here it is shown that it is rotating in clockwise direction. Theta is the angle of lap. Here this angle, this complete angle from here to here. Also, it is also known as warp angle. Force is applied in upward direction. So start with the design. Let us consider this new free body diagram for the band and wheel arrangement. If wheel is rotating in clockwise direction, then this band ends, one end will be having tension T2 and another tension T1. This T1 and T2 will generate some torque. Let us say this T1 is generating counterclockwise torque equal to T1 into R. R is the radius of the wheel. Whereas T2 is generating torque in clockwise direction equal to the T2 into R. So to stop or slow down the clockwise rotation or movement of wheel, we need to get the resultant of this both T1R into T2R and T2R. That means the torque due to T1, tension T1, and torque due to tension T2. So resultant of this torque will be the braking torque, will be equal to T1 into R minus T2 into R. Now, so braking torque will be T1 minus T2 into R. As we know, we have given name T1 or annotated T1 to the tight side and T2 to the slack side of the band, right? So keep in mind or remember this, T1 should always be tight side tension and it should be greater than the T2. D2 is the slack side tension and it will be smallest as you will go, let us say here from this point of contact from T1, the tension will go on decreasing up to T2, or in other words, if you move from T2 or this point of contact, this tension at this band, at this point in the band will be T2 and will be smallest and will go on increasing as we will move like this towards this point of contact, and here will be the tension T1 which will be maximum. So how will be this variation of the tension in the band? So that tension over the band length, this length of the band along the surface of the contact with wheel, that means up to from this to this where there is a contact with the wheel. T reduces from T1 towards the T2, like here from T1 here to here it will be reducing value in the tension. So highest tension is T1, which is greater than T2, and T2 is the smallest tension at theta T. Let us start from this side where there is a tension is very small, and if we will see the angle subtended from here to here, there will be a theta. It will go on increasing theta. Let us say very small angle theta is there between these red lines. So at this very right point, very right side end of the point of contact with the wheel, the band is making angle theta equal to 0. At that point tension will be T equal to T2, and at this left extreme left end theta will be equal to the theta max, and tension at that point T will be equal to T1. Now to find this relation between T1 and T2 and the variation, how this T1 and T2 or the tension value along the length of the band will go on varying, or either it may be increasing or decreasing, we will use the static equilibrium equations. As we know that this band is in static condition, it will not rotate, so we can use this static equilibrium equations. As we have seen in previous figure, that the red lines were making very small angle d theta, so we have drawn the exaggerated figure of the same d theta, so that here if I will divide this d theta angle, complete angle d theta, I will get left half equal to d theta by 2 and right half angle will be equal to d theta by 2. Now here you can see this is the T, and from this right extreme right end the tension will go on increasing up to this left extreme left point, where the increase will be the increase in the tension will be dt. Previously it was only T, and addition is dt, so final tension at this extreme left end is T plus dt. Now we will find the forces in x direction and y direction for equating these equilibrium equations, or finding this relation between T1 and T2. For that I need to find the x component and y component of this T and T plus dt. For that I will use these angles and some trigonometry formulae. If I will extend this T1, here you can see this is the line of action of T, and this is the radius. Here you can see this is the radius, and angles obtained by these two radii will be d theta by 2. Similarly I have drawn it here. You know that if this and these two lines are making angle 90 degree, and one vertical line is making an angle of d theta by 2, any angle, let us say x, then this angle and this angle will be same. So we have got this angle. Now we will find the cos component or the sine component of the T, and we will use those sine component and cos component for finding the or equating the values for this equation. Let us say summation f of x equal to 0 and summation y f of y equal to 0. So start with the summation f of x equal to 0, t cos d theta by 2, that's the cos component of this t in the x direction, plus mu r, that is fb, plus equal to the cos component of this total t plus dt will be t plus dt into cos of d theta by 2. Finally we have got mu r equal to dt cos d theta by 2. Similarly we will do for summation f of y equal to 0. Before that we will put the values of cos d theta by 2. As you know that d theta is very small and again we are dividing it by 2, so let us say it is very small value, close to 0, let us say, because smallest angle is 0, and you know that for minimum or smallest value of cos theta is 1. So we will consider it equal to or near to 1, not exactly 1 but very close to 1, and we'll put that value of cos 2 theta by 2 equal to 1 in our previous equation for the which we have got from summation x f of x equal to 0. Here we are getting equation qr is equal to dt, let us say equation 1. Now we will do summation of y or equate summation f of y equal to 0. Again sine component of t and t plus dt, we will get this value r equal to t d theta into plus dt into d theta by 2. How we have got this sine d theta by 2 equal to d theta by 2? Because you know that for very small angle the value of sine theta or sine x, let us say, will be equal to x. From that we have written it, and you know that if a very small value, let us say 0.001, is multiplied by again with very small value, the multiplication will again come smaller than that, so we can neglect this part or multiplication factor, right? From here we are getting the value for r equal to t into d theta. Putting this value of r equal to t into d theta in the equation 1, so what we will get, mu into t into d theta is equal to dt. We'll see in next slide. Here we have put the value of r equal to t d theta and we have got this equation. Now we know that the value of t, that is tension, varies from t2, that is smallest value, up to the t1, that is maximum value. So lower limit will be t2. Now integrating this equation on both sides, integral t2 to t1 d theta dt by t equal to integral 0 to theta of mu into d theta. Finally we will get, by solving this, ln, that is log t1 by t2 is equal to mu theta, and the relation between t1 and t2, how this t1 and t2 is varying along with this theta, we have got this relation. And this, along with this equation, one more equation will be very important to solve the band brake system or the design of band brake. Keep in mind this theta is not associated with trigonometric function, so it will be always in radians. First equation this, and second equation for braking torque t1 minus t2 into r. Both these equations are there containing t1 and t2, so from this second equation we will get the variation along with the theta, and final braking torque we can find from if we are getting relation in t1 and t2 by putting this value for t1 in terms of t2, or putting the value of T2 in terms of T1, we will get the answer. T1 is the tight side tension, and divided by T2, that means slack side tension, will be equal to E mu theta, which I have recently proved. Now we need to also design the band. How will be the band material, which band material, and what will be its strength. So design of band, we will design band for critical tension condition, that is maximum tension, and we know that T1 we always annote as maximum tension. For safe design, we will do it or design it for the critical tension. As band is under tension or tensile load, so the failure will be tensile failure, and the induced stress will be tensile stress or normal stress. So from this figure you can see the B is the width of band, and T here, T is the thickness of the band. So cross sectional area will be B into T, and force on that will be T1, tension force. So a normal induced stress will be force upon area, that is T1 by Bt. So this induced stress should be less than the yielding strength of the band material, or it can also be called as a permissible maximum stress value. Here we have got the relation for the design of band, that is T1 by Bt should be less than equal to Syt. Now we will see the two cases for the arrangement of fulcrum lever and the rotation of the wheel. First is the when this moment at the fulcrum due to the any of the tension T1 or T2 is 0. Let us say if the line of action of T1 or T2 is in the line of or in line with the fulcrum, then moment due to this, let us say here I can say T2 or T1 into this distance will be the moment, and for T2 moment will be T2 into distance is 0 because fulcrum is here. So this moment due to T2 will become 0, either due to T2 or either due to T1, always there will be a moment 0. So only remaining is the T1 will remain or T2 will remain. Such time of arrangement is nothing but the simple band brake, and we will again discuss the how differential band brake is designed. For time being, you just concentrate here. The moment due to any of the tension is 0, and here or in first case the wheel is rotating in clockwise direction. So we know that braking torque will be T1 minus T2 into R, and another formula for getting relation between T1 and T2 is T1 by T2 is equal to E mu theta. Any of the three values from T1, TB and T2 will be asked to find, and another two will be given, or some information regarding them will be given. So what will be the required external force or applied force or effort to stop the rotation of the wheel? For that we will equate or use the static equilibrium formula, as the band is not rotating, so that is band is static. So formula for static equilibrium is epsilon or summation of moment at fulcrum point O equal to 0. From figure you can see F was acting downward direction and its distance was L from the fulcrum. So, F into L minus T1 on the right side. T1 into A. A was the distance of tension T1 from the fulcrum, and T2 was in line with the fulcrum, so moment due to T2 will become 0. So here we are getting F equal to T1 by L. This is the equation number 1. And similarly in case 2, either T1 or T2 moment due to T1 or T2 is becoming 0, and here the difference is that in previous case 1 the rotation was clockwise, here the rotation is anti-clockwise for the wheel. So similarly, by equating moment at fulcrum equal to 0, we will get external applied force or effort equal to F equal to T2A by L. Now given question is that whether clockwise or anti-clockwise rotation is desirable for minimum effort. That means whether the minimum effort will be required for braking in case of clockwise rotation of wheel or anti-clockwise. So we will find it from equation 1. This for clockwise rotation, F1, let us say force, applied force is F1 equal to T1 by A, T1A by L, and for counterclockwise rotation of wheel, applied external force F2 equal to T2A by L. From here we have find it from this equation, moment of summation of moment equal to 0. Now you know that T1 is greater than T2, and in this F1 and F2, A by L is common thing, just difference is T1 and T2. If T1 is greater, that means F1 is greater than F2. So for minimum effort, F1 and F2 are the efforts or applied forces, and we want minimum force. So you can see here F2 is lesser than F1, that means minimum. So this F2 will be desirable, minimum value will be desirable, acceptable, or good for the braking. That means at less efforts you can stop or reduce this force of the reduce the speed of the wheel. So answer is the drum should rotate in counterclockwise direction. For minimum effort, sense of rotation of wheel, drum or ring should be counterclockwise in simple band brake. Now in simple band brake you cannot get self-energizing property, or simple band brake cannot be self-energizing, as the resultant moment of or I can say the resultant moment due to the tension T1 and the moment due to the tension T2, let us say TB1 and TB2, right, or TR1 and TR2, resultant of this TR1 and TR2, let us say some another moment you are getting, and it is equal to 0 because fulcrum is in line with the either the T1 or T2. So moment due to any one tension becoming 0 and another is remaining, and that moment due to another remaining tension will always oppose the applied braking force. Let us say here is the drum and these are T1 and T2 values, or any of the, here you can see, let us say here is the fulcrum and this is the our lever. This portion is becoming 0 because distance from the fulcrum is 0. Now let us say this is a T1. Now you can see that this will always oppose whether it is T1 or T2 depending on the clockwise or anti-clockwise direction of rotation of the wheel. This always oppose the applied force F. So this type of simple band brake can never be self-energizing. Hence, to make the band break self-energizing, fulcrum should not be in line with T1 or T2, neither with T1 nor with T2, and resultant of movement due to T1 and movement due to T2 should assist applied force for braking. That means whatever be resultant due to T1 and T2. Let us say I am taking fulcrum here now, new fulcrum. Okay. Now the moment due to this T1 or T2 will not be 0 because they are not in line to fulcrum. Now resultant or summation of this T1 moment due to T1 and T2 will be some value, and that should assist, or that should be in direction of the moment due to external force. Then and then only such type of brake will be self-energizing. Then is it the thing that whenever we will keep a fulcrum not in line with any of the two, let us say I am keeping fulcrum somewhere here, then will it always be a self-energizing? The answer is no, right? But many are in, it can be self-energizing, not always, but it can be, right? So design for differential brake, we will start from here, and by replacing the position of this fulcrum. Now whether we should apply force to create counterclockwise moment, or we should apply force in the downward direction instead of upward direction to generate a clockwise moment. We will see. Let us say this distance A is representing the distance of tension from the fulcrum. Let us say this is tension, any tension T1 or T2. Then distance from this tension, line of action of this tension to the fulcrum is A, and similarly this distance from line of action of this tension to the fulcrum is B. And in this first case we are assuming that force, direction of force is upward, external applied force is upward. Now assume that if we will push this or pull this lever upward, then what will happen? There will be little elongation, let us say, in this band at this side, and whereas at this side there will be as compared to higher elongation, let us say. So and this angle theta will be same because these are opposite angles. So if we will use the trigonometry, what we are getting, let us say this elongation is y and this elongation is x. Tan theta is equal to y by b is equal to x by a. So x by a equal to a by b. You know that a is greater than b here. This a distance is greater than b distance. So their ratio will be greater than 1. So x by y is equal to y is greater than 1. That means x will be greater than 1. Then that means slack tension in slack side, or the loose band length is greater than the tight band length y, right? So it is there will be no braking, right? So we want this opposite of this situation. So how we will get it? We will change the direction of this applied external force. Now in this case you can see this is the direction of applied force, and let us say our fulcrum will move to this position, this dotted line, finally to this position, this second dotted line. So there will be let us say y length or elongation in this band end, and where at the band end on this left side there will be x length. So again, using the same trigonometry, here we will get the same angles on both the side, theta, let us say. Okay, here this will also be equal to theta. So tan theta is equal to x by a is equal to y by b. So x by y equal to a by b, and you know that here a is again greater. A is greater than b, so a by b is ratio a by b is also again 1. But here x is the distance on the upper side because we have changed the direction of the force. So x is greater than y, and in previous case it was also the same, but you can see x was also greater in this case, but it was the loose band, x was the loose band length, and y was the tight band length. Now, but in case 2, here the y is the loose band length and x is the tight band length, right? So this is the correct direction of applied force. Now as we have got the correct direction, we will now apply the static equilibrium to this band, as this band is static, and we will get the values for applied force and related conditions for self-analyzing and as well as for self-locking. First, write the equation for moment, summation of moment at O, that is fulcrum, equal to 0. So we will get FL plus T2A is equal to T1B. So F is equal to T1B minus T2A by L. And for self-locking condition, that means we need not to apply any force, that means force will be 0. And for that, if force is 0, if we will put it 0 in this equation, we get the relation between T1 and T2. It will be T1B equal to T2A, and in such condition the brake will be self-locking. This is the condition for the self-locking of a band brake, and this was all about the design of band brake. If you have any doubt, you can comment in the comment box. So thank you for watching the video. Till then, you can enjoy these lectures or repeat these lectures if you have doubt, or wait for the next lecture. Till then, I will be in touch with you. Thank you for watching once again. Signing off for the day.